Hey students, how you doing today? Elliot with a brand new hat is here today to teach you about your brand new parent function, the exponential equation parent function. That is an equation of the form y equals a to the x, and say you wanted to graph it. I'm going to start off with graphing y equals 2 to the x, making a table of values. And I'm going to start with some of these values down here that actually I know really easy. Let's see. 2 to the 1. 2 to the 1 is 2. 2 to the 2. 2 times 2, that's 4. 2 to the 3. 2 times 2 times 2 is 8. 2 to the 0. Well, I know it's equal to 1, and maybe you know it's equal to 1, but if you don't know it's equal to 1, check this out. There's a pattern. How do you get from 8 to 4? How do you get from 4 to 2? You could say dividing by 1 or dividing by 2 or multiplying by 1/2. I like multiplying because we're dealing with exponential equations. 8 times a half is 4. 4 times a half is 2. 2 times a half is 1. So 2 to the 0 power is 1. What about this one? 2 to the negative 1. Well, if you follow the same pattern, multiply by half, multiply by half, multiply by half, 1 times a half is 1/2. So 2 to the negative 1 is equal to 1 over 2. 2 to the negative 2. Well, if you take 1 over 2 and you multiply it by 1/2, you get 1 over 4. Oh, I think I see the pattern. 2 squared is 4, so 2 to the negative 2 is 1 over 4. So that means that 2 to the negative 3, that must be equal to 1 over 2 to the positive 3, which was equal to 1/8. Okay, I have enough information to go ahead and plot this graph. But before I really graph it, I need to show you this thing. This graph has a dotted line. And this dotted line is called an asymptote. Asymptote. When you pronounce it, I think the P is silent. So asymptote. And our asymptote in this particular case is along y equals 0. Because if you think about it, 2 to the negative 3, 1 over 8, that's a very small number. 2 to the negative 4 is going to be 1 over 16, an even smaller number. 2 over 50, or 2 to the negative 50, that's going to be even smaller. 2 to the negative 100, even smaller, smaller. But we'll never actually reach negative. So when we draw our graph, we draw it like this, because as x got very, very small in the negatives, or negative big, you got very, very small numbers. So the graph is going to hug the asymptote. And that's what an asymptote does, is it shows you where the graph is going as x gets very, very large in either the positive or the negative direction. So in this case, as x gets large in the negative direction, the y value gets closer and closer to 0, but never quite reaches 0. So we put this asymptote to demonstrate that the graph will never actually touch y equals 0. Now, remember how our previous chapter had key points? We also have key points. We have a key point at 0, 1. We have a key point at 1, 2. And then we have a third key point at negative 1, comma 1/2. So those would be, this would be the parent function for y equals 2 to the x. So your parent function with exponential graphs will actually change depending on what this number is. So if it was 2 to the x, this is your parent function. But let's say it was 3 to the x. Well, the two graphs will have the exact same look. There will be this horizontal asymptote along y equals 0. You do need to physically write y equals 0 every single time, by the way. But the two graphs will essentially look the same. And if you plug 0 into this equation, 3 to the 0, you still get 0, 1. But the difference is that instead of this coordinate being 1, 2, this coordinate would be 1, 3. And then over here, instead of being -1, -1/2, would be -1, -1/3. So your key points are going to change depending on what your base number is, what your constant multiplier, not constant multiplier, what your use the right word, Elliot. The common ratio. They have the same common ratio. Okay, so these are for growths. 2 to the x, 3 to the x. Our common ratio is bigger than 1, so we have a growth. What if it was a decay? So for example, number 3. What if it was y equals, instead of 2 to the x, what if it was 1/2 to the x? Well, we can make the exact same table of values that we made before. -3, -2, -1, 0, 1, 2, 3. And same thing, let's start with the ones that we're familiar with. 1/2 to the 1, that's equal to 1/2. 1/2 to the 2, 1/2 times 1/2, that's 1/4. 1/4, or excuse me, 1/2 to the 3, 1/2 times 1/2 times 1/2, that is equal to 1/8. Are you noticing something? This is very similar to the 2 to the x, those negative values that we got. Interesting. All right, well, anything to the 0 power is always equal to 1, and if you follow the pattern, to get from here to here to here to here, it was multiplying by 1/2. So if you travel in the other direction, think reciprocal. So multiply by 2, multiply by 2, multiply by 2, multiply by 2. So 1/2 to the -1 is equal to 2. 1/2 to the -2. So how I think about it is you reciprocate the fraction, and then that makes the exponent change from negative to positive. So 2 over 1 to the positive 2, that's equal to 2. Or once again, multiplying by 2. 2 times 2 is 4. So the next number will be 8, because 1/2 to the -3 is the same thing as 2 over 1 to the positive 3, which is equal to 8. So what's that mean? Well, as x got positively big, the graph kept getting smaller and smaller and smaller, but never quite reached 0. So you still have this asymptote along y equals 0. Make sure you label that asymptote. But then instead of being an exponential growth, like our first couple graphs, this is an exponential decay, where the graph is getting closer and closer to the asymptote, but it never quite reaches it. And you have these same key points at 0, 1, -1, 2, and 1, 1/2. Okay, so the last thing I want to talk about is, well, this is what our graph looks like for it was 1/2. Oh, I guess I should quickly do a follow-up. What if instead of being 1/2, let's say it was 1/3? Well, this number is in between 0 and 1, so you know it's a decay. So you can draw in the decay, write the asymptote along y equals 0, and then you have a key point at 0, 1. 0, 1 will always be a key point in these exponentials. And then instead of, and if you plugged in 1, it would be 1/3. And if you plugged in -1, it would be positive 3. Did I just say -1/3? I meant positive 1/3. So the numbers change depending on what your base was. Okay, so last thing I want to talk about. Oh, I promised this lesson would be under 10 minutes. I think it's going to take maybe 11 or 12 minutes now. Is what's the difference between 2 to the x and 1/2 to the x? So fifth thing I need to talk about, the last thing, is 2 to the x versus 1/2 to the x. Well, if we compare our two graphs, our 2 to the x was the growth with these 3 key points. Our y equals 1/2 to the x was the decay, and the points are just getting flipped around. So instead of -1, 1/2, it's -1, 2. Instead of 1, 2, it's 1, 1/2. so the y-coordinates are essentially flipping with each other. And if you compare this 1, 2 to negative 1, 2, that looks a lot like x is changing. That's a y-axis reflection. 0, 1, that would just reflect, a y-axis reflection would just reflect 0, 1. But negative 1, 1/2, that's a y-axis reflection. So 2 to the x and 1/2 to the x. You have very similar graphs, except you have these key points are like they are y-axis reflections. And if you look at these two graphs, they kind of look like y-axis reflections. So you have two options here. Option 1 is to memorize two different parent functions for exponential. You'll have the growth equation that will look like this, or you have the decay equation that looks like this. So you have two separate parent functions. Parent function 1, parent function 2. So you kind of have two parent graphs that you need to memorize. That's option 1. Two separate. Option 2. And in this particular case, like usually I do have an opinion of which one I prefer, but like with team graph paper, team non-graph paper, I was trying to push you to be team non-graph paper. I don't know in this case which option is better, option 1 or option 2. Option 1, you would only think about one parent function. You think about 2 to the x. Oh, I forgot to label my asymptote up here. So you would have your parent function y equals 0, and then you'd have your three key points, 0, 1, 1, 2, and negative 1, comma 1/2. So in this case, I'm going to think about 2 to the x only looking like this. Now, 1/2 to the x, as we talked about earlier in our table of values, if you reciprocate the function, the exponent that's attached to it becomes flips from negative to positive. Or it could also go in the other direction, going from positive to negative. So I could just think of 1/2 to the x as being the same as 2 over 1 to the negative x, or simply 2 to the negative x. And if you think about, well, what's 2 to the negative x compared to this graph? It's just like 2 to the x, except there's a y-axis reflection. Think coordinates. That means that your xy would become negative x, positive y. So this coordinate 1, 2 would become negative 1, 2. The point 0, 1 would stay 0, 1. And the point negative 1, 1/2 would become positive 1, 1/2. So you could just use this. When Elliot has a choice, he chooses option 2. I only like to memorize one parent function, and then I like to think about y-axis reflection. So when I'm given an equation like this, I alter the equation so that it looks like this, and then I graph this equation. Other option is to simply memorize that there's exponential equations, that there's two separate parent functions. One thing that's nice about option 1 is if you do option 1, you will never have to worry about a y-axis reflection because it's not going to happen, because you don't put y-axis reflections in with the growth or decay. Or if you think about it this way, that there's only one parent function, which is a growth, the advantage is that you only have to memorize one parent function. The downside is that you are going to have to memorize a y-axis reflection. So 2 parent functions, never have to worry about y-axis reflection, or 1 parent function and you do have to worry about y-axis reflections. That's the decision for you to make, everybody. So tomorrow in class, I am going to graph some examples. And oh, this was no, this is part of example 5. So I'm gonna have 3 or 4 examples to do for to show for you, and I want to get these equations onto paper now. Let me write these down so that you can be prepped for them if you so desire. Number 1, it's going to graph y equals 4 to the x minus 3 plus 5. Uh-oh, you can't see it because of Big Elliot. The second equation we're going to graph is y equals 1/8 to the x minus 6. Number 3, y equals -6 to the x plus 4. And number 4, we're going to graph y equals 1/4 to the x minus 3 minus 2. So these are the 4 we're going to graph tomorrow in class. So we're going to graph these 4 as a class, putting examples up on the board, and then we're going to take that quiz, and then we're going to start practicing. So I hope everybody, you have yourself a fantastic evening, and I will see you tomorrow on Tuesday. Bye-bye.